Record. Okay, so then we're going to finish off chapter 4 on energy. So the chapter 4 homework is due on the 19th. That's next week, Wednesday. The chapter 4 quiz will also be on the 19th. That is also next week, Wednesday. The week after that, on Monday, we will have a test on chapters 3 and 4. So not next week, but the week after, we'll have a test on chapters 3 and 4. So we've been doing work and kinetic energy. Work is force times distance. Force in the direction of movement times distance. Work on an object causes it to gain kinetic energy. Kinetic energy is 1/2 mv squared. So the work done on an object equals the change in kinetic energy. So 1/2 mv final squared minus 1/2 mv initial squared. Additionally, there is potential energy. Potential energy is the energy stored in an object's position. Potential energy will be mgh, because we're only going to deal with gravitational potential energy. There are other kinds. There's, electrical, magnetic, spring forces are the most common one you're going to run into. But in this class, we're only going to deal with gravitation. So when you lift something up into the air, it gains potential energy. You can get that energy back by letting it fall. So for example, if you toss something into the air, it loses potential energy, it gains potential energy and loses kinetic energy as it goes up, and then it gains, and then it loses potential energy and gains kinetic energy as it comes down. So on the way up, potential energy is increasing and kinetic energy is decreasing because it's slowing down. On the way down, kinetic energy is increasing, potential energy is decreasing. So that's conservation of energy. Energy can either be created or destroyed. It just goes from one form to another. So the total energy of an isolated system will remain constant. That means the total energy at time 1 will equal the total energy at some later time, time 2. So the total energy will not change with time. And in general, what that's going to mean is, initial kinetic and potential energy equals final kinetic and potential energy, at least for the problems we do in this class. So we can simplify it. We'll deal with ideal systems. So kinetic and potential initial at time 1 equals kinetic and potential, kinetic plus potential at time 2. So you have the transfer of energy from kinetic to potential or from potential to kinetic. Now, we're doing all this work. We're moving energy around. Sometimes we want to talk about the rate at which we're moving energy around. So the rate at which energy is moved is power. It's the rate of doing work. So power is work over time, or force times distance over time, which means for certain situations, it ends up being force times velocity. But that's only in certain situations. The units for power, so, units for energy and work are, 1 kilogram meter squared per second squared, which is 1 Newton meter or 1 joule. Power, 1 joule per second is 1 watt. So the unit for energy is the joule per second, because it's energy for, it's work over time. And so the unit is 1 watt. So a 100-watt light bulb uses 100 joules of energy every second. And be careful not to confuse work with watts. One is a unit, one is a variable. In power, the unit is watts. You've probably seen this all over on electrical devices. They're labeled in watts. So if you use a force of 1 Newton to raise a mass a distance of 1 meter, the amount of work done is 1 joule. And if this work is done in 1 second, then the power is 1 watt. The most likely place you'll see power ratings is on electrical devices. And that's how many joules per second they use. So here's a review of the units. Units, a Newton for force. The unit is the Newton. The symbol is a capital N, and it's a kilogram meter per second squared. Work is a joule, which is a Newton meter. So it's a kilogram meter squared per second squared. That's the same for work and energy. And power is a watt, which is a joule per second. Power is named after James Watt, who greatly improved the steam engine. And also invented the unit of horsepower. You may have seen the unit of horsepower. The unit of horsepower is a unit that James Watt invented to sell steam engines. So it is not the most accurate measurement of the power of a horse. For example, I watched a video recently that showed that a draft horse can output something like 6 or 7 horsepower when connected up to a dyno. It was a car show. But the idea of it was that it was supposed to be the average power output of a horse over a day, like working at some industrial site as a power source. It was a description of how many horses the engine could replace, basically. But the horsepower is defined as 550 foot-pounds per second. And it's about 750 watts. So in work, in the British system, work is measured in foot-pounds. Power is in foot-pounds per second. The common used unit for power in the British system is the horsepower, and it is 550 foot-pounds per second, or 746 watts. So the greater the power of an engine, the faster it can do work. So a 2-horsepower engine can do twice the work of a 1-horsepower engine in the same amount of time. So here's an example of calculating power. Constant force of 150 newtons is used to push a student's stalled motorcycle a distance of 10 meters along a flat road in a time of 20 seconds. So here, for power, we can find work by doing force times distance, and then find power by dividing that by time. So force is 150 newtons, distance is 10 meters, time is 20 seconds, power is work over time, or force times distance over time. So 150 newtons times 10 meters over 20 seconds. 150 newtons times 10 meters is 1,500 joules. divided by 20 seconds gives us 75 watts. Here's another example. If a student expends 7.5 watts of power, lifting a textbook half a meter in 1 second, how much work was done, and how much does the book weigh in newtons? So here, once again, power is work over time. Since power is work over time, work is power times time. So power is 7.5 watts, the distance is half a meter, the time is 1 second. Work will be power times time, so 7.5 watts times 1 second, which gives us 7.5 joules. There's 7.5 joules of work lifting this book. And work is force times distance, so the force will be work divided by distance. So 7.5 joules divided by 0.5 meters gives us 15 newtons of work. Weight, sorry, bad. The book, he applied 15 newtons of force to do that 7.5 joules of work. So the general idea here is that, power is work over time. So work is power times time. And work is force times distance. So force work over distance. Now, for electrical energy, we talk about how much energy is produced or consumed over the time taken to talk about the power. We rearrange this. The electrical energy used is power times time. So much like work is power times time, energy is power times time. Energy moved or energy used is power times time. Name? Since power is given in watts, power times time will be in joules, because watts are joules per second. So joules are a unit of work or energy. However, if you look at, say, your electrical bill, got one of those. The power you consumed, or the energy you consumed, will not be listed in joules. On your electrical bill, you will use kilowatt hours. That is still a power times the time. So 1 kilowatt hour. Let's figure out how many joules 1 kilowatt hour is. Well, it's 1 kilowatt times 1 hour. So we can think of this as 1 kilowatt times 1 hour. 1 kilowatt is 1,000 watts. 1 hour is 3,600 seconds. So 1 kilowatt hour is 3.6 million joules. And considering that your average electrical usage is in a reasonable number of kilowatt hours, you can see why we don't measure our electrical usage for electric bills in joules, because the numbers would be enormous. So 1 kilowatt hour is 3.6 million joules. We could measure electrical pay in megajoules, for example, but also I think historically it was easier to measure kilowatt hours for practical purposes than megajoules. Name? So that's kilowatt hour. If we want to figure out how much energy is consumed by some device, well, let's say we have a 1 horsepower electric motor that runs for 10 hours. So we want to figure out how much energy gets used by this in kilowatt hours. Power is 1 horsepower, time is 10 hours. So we want to convert power from horsepower to watts to kilowatts, and then multiply that by the number of hours. So 1 horsepower is 746 watts. 1 kilowatt is 1,000 watts. So 746 watts is 0.746 kilowatts, or 0.75 kilowatts to keep the same number of significant figures. 0.75 kilowatts times 10 hours is 7.5 kilowatt hours. And we could do the same thing in joules and find out how much that is. We just multiply by 3.6 million, basically. So if I use 55 newtons of force to push a box a distance of 5 meters in a time of 22 seconds, how much power am I producing? So power is work over time, which means power is force times distance over time. And now we can just plug in our numbers. 55 newtons times 5 meters divided by 22 seconds. That gives us 12.5 watts. If it takes a 2,500 watt oven 30 minutes to cook a pizza, how much energy is necessary to cook the pizza in joules and kilowatt hours? So there's some unit conversions here. 1 minute is 60 seconds. 1 hour is 60 minutes. 1 kilowatt is 1,000 watts. Basically, we need to do this in 2 ways. One, to find joules, you want to multiply watts by seconds. To find kilowatt hours, you want to multiply kilowatts by hours. So you'll need to convert the time into both hours and seconds, and convert the power. You'll need it in both watts and kilowatts. So power is energy over time, so energy will be power times time. So let's start by converting the times. 30 minutes is equal to either 1800 seconds or half an hour. So let's start by calculating the value in joules. We have 2,500 watts times 1800 seconds. That's 4.5 million joules. 4.5 times 10 to the 6. Here, we do it in kilowatt hours. 2,500 watts is 2.5 kilowatts. The 2.5 kilowatts times half an hour is 1.25 kilowatt hours. Lastly, we can check that these numbers make sense by converting 1.25 kilowatt hours to joules. 1.25 kilowatt hours times 3.6 times 10 to the 6 joules per kilowatt hour gives us 4.5 times 10 to the 6 joules. And here, how high can a 1 horsepower motor lift a 15 kilogram mass in a time of 2 minutes? So remember, to get the force required, you'll need to multiply 15 by 9.8. And you'll need to convert the time from minutes to seconds and the power from horsepower to watts. So 1 horsepower is 746 watts. We can now calculate how much work 1 horsepower motor is going to do in 2 minutes. 2 minutes is 120 seconds, with 1 minute and 60 seconds. So work is power times time, which equals force times distance, which equals mg times h. So the height is going to be power times time divided by the weight, mg. So 746 watts times 120 seconds divided by 15 kilograms times 9.8 meters per second squared comes out to 609 meters. So 1 horsepower is a lot of power, actually. I should probably rewrite this question to be 150 kilograms. If you calculate the work first, it's 89,520 joules over 147 meters. And here, how much power is expended by a 60 kilogram man climbing 15 meters in 30 seconds, which is pretty dang fast. But they're nice round numbers. This is fairly straightforward. Power is work over time. Work is force times distance. The force required is going to be the mass times weight. So this is going to be mgh over time. 60 kilograms times 9.8 meters per second squared times 15 meters divided by 30 seconds comes out to 294 watts. And if it takes 100 newtons to keep a car traveling at 11 meters per second, how much power is the car using to do so? So remember, power is work over time, which is force times distance over time. And distance, if something's moving at constant speed like this, is just going to be velocity times time. So for this, to figure this out, the trick is you can choose an arbitrary time. That's one way you can approach it. Power is work over time. We can say, let's look at 1 second of traveling here. So power is force times distance over time. So force times velocity times time divided by time. Time will cancel. You'll actually find that power is force times velocity. But the other way you can approach this is you can say, let's say this car travels like this for a second, 100 newtons times 11 meters per second times 1 second. 11 meters per second for 1 second is 11 meters. 100 newtons times 11 meters is 1100 joules. 1100 joules divided by 1 second is 1100 watts, which is 100 newtons times 11 meters per second, or 1100 watts. Now, no matter what type of energy we talk about, chemical, electrical, mechanical, the main thing here is that energy is conserved. Energy is converted from one type to another. And almost always, when it looks like energy isn't conserved, when it looks like you're losing energy to something, that energy is usually being turned into heat. And you can show this. You can do something like run paddles in a bucket of water, and that water will warm up. Or, you can rub your hands together. That's like wasting energy, and your hands warm up because it's being converted into heat. So we can either create or destroy energy, but we can convert it from one form to another. So some forms of energy. Thermal or heat energy is related to the kinetic and potential energies of stuff on a molecular level. Heat is the energy in atoms jiggling around and bouncing around, and so the kinetic and potential energy. Thermal energy is the kinetic and potential energy of stuff on the atomic and molecular scale. So like heat, your temperature is a measure of like average kinetic energy. So the faster stuff is moving around, the higher the temperature is, the particles. And then gravitational potential energy is a measure of the energy of an object's position. That's stored gravitational potential energy. You get that by lifting something up. Electrical energy is the energy associated with the motion of electric charges. So we use energy from moving electric charges around to generate energy. Chemical energy is energy stored in molecular bonds. It's potential energy tied to the formation and breaking of chemical bonds. Radiant energy is electromagnetic energy from the sun. And so electromagnetic energy is just light. Light transfers energy. It's a wave of electric and magnetic fields. Nuclear energy is energy released by, tied to the rearrangement of nuclei. There's fission, where you get energy by breaking larger nuclei into smaller nuclei. That's what happens in your average, everyday nuclear power plant. They take big nuclei of uranium and cause them to break into smaller. They break them basically in half, and it releases energy. And you can do the opposite. You can take small nuclei and bind them together. So for light stuff like hydrogen, it releases energy when you merge them together to form a heavier thing like helium. For heavy stuff like uranium, when you split them apart, it releases energy. And the balance point for nuclei happens to be at iron. Then there are fossil fuels. Fossil fuels are supplies of stored chemical energy generated from solar energy from plants. The fossil fuels, all oil, gas, coal, are all stored chemical energy from plants that were buried millions of years ago. So gas and oil comes from marine organisms that were buried and converted. Coal all comes from plants. Pretty much all the coal in the world is from around the same time, around 350 million years ago. The oil comes from marine organisms. Those numbers are not accurate because they're old and outdated. Gas also comes from marine organisms, again, that were buried and decayed and converted and fossilized and turned into gas. And then coal comes from terrestrial or land plants. And lastly, methane hydride is a crystalline form of natural gas and water, which is being studied for a couple of reasons. We don't want it to accidentally be released by global warming, because it's basically methane trapped in ice. So if it warms up, it melts, the methane gets released, and methane's a powerful greenhouse gas, so that would be bad. And just in general, fossil fuels aren't the greatest source because the supply is limited, and their burning releases greenhouse gases, which contribute to climate change and warming of the system. And coal is just even worse. Coal is coal releases all kinds of terrible waste, and in fact, releases more radioactive. Coal burning power plants release more radioactive waste than nuclear power plants, and they do it into the air where they gets exposed to people. Like, But here are some examples of extraction. These are pump jacks pumping out crude oil for fossil fuel. Here's a Christmas tree. This is a gas well. Gas wells don't need to be terribly complicated because they're generally under pressure. So you basically drill a hole into the gas and just let it go into a pipe. Here's a coal bed. This is a layer of coal. Now, we also get energy from food. Food is stored chemical energy from other living things that we eat. These are some somewhat out of date stats on US fuel consumption. Natural gas has gone up, coal has gone down, renewables have gone up since this chart was made. This is from like, oh God, it's almost a decade old, I think. No, this is, no, I got this more recently. This is only a few years old, I think. I don't know, I have to go. I mean, this is from your text, but this was like from an older edition, I think, originally, but these charts may not be up to date. Because this stuff changes over time. Renewables has gone way up, especially since solar got cheap. And coal has dropped quite a bit because coal stopped being so inexpensive. For electrical generation, definitely this is a big thing. Coal has gone down. Various renewables have gone up. Natural gas has gone up. Hydroelectric has not probably changed. Nuclear is, if anything, probably gone down, unfortunately. And here's some rough energy consumption by sector. Industrial consumption and transportation are the two biggest consumers of energy, then residential and commercial. Now, alternate and renewable energy sources are energy sources, alternate energy sources are energy sources not based on fossil fuels or nuclear processes, and renewable energy sources are ones that can't be exhausted. And in a large part, these overlap. So, hydropower uses the gravitational potential energy of water to do work to generate electricity. The water flowing downhill, pulled by gravity, spins turbines, generates electricity. Now, the biggest problem with hydropower is that you got to build a dam and pile up a whole bunch of water somewhere, and all the good sites are already done, taken, built. It does a surprising amount of environmental and ecological damage from the whole area that gets flooded by building the dam, and various other factors like that. It's not great. It also has a tendency to flood agricultural land. It causes big loss of agricultural land. But yeah, all the best sites for hydro dams are, they already got dams on. And it does some weird things to the flow of stuff in the river that you put a dam on. There's all kinds of complications. And they're not terrible or anything, but they are a thing you have to deal with. But so this is the Flaming Gorge Dam in Utah. You know, this big reservoir here. Just there's things you have to pay attention to for dams. They're big, expensive projects. And again, all the really good sites are taken. Because yeah, the best sites for hydropower installations are things like in narrow canyons, so you don't flood huge areas. We filled those all up in the US, basically. Wind power. Now, wind power isn't particularly aesthetic. Big, giant wind turbines. It needs to be located where the wind is sufficiently constant and strong enough. It's inconsistent. Big problem with a lot of renewable energy sources is you're dependent on what's happened in the nature of the wind. It has minimal environmental effects, and it's been used for thousands of years to do various forms of work, to grind grain, to pump water. You know, that's why there's all those windmills in the Netherlands, because they're pumping all the water out to reclaim the land. Much of their country is below sea level. So it's not particularly aesthetic, but otherwise it's pretty good. Biggest problem is that it's inconsistent. So the biggest problem with a lot of these is that they don't generate power on demand. And our grid works on power on demand. It doesn't have any sort of storage built into it. So the electrical grid needs storage, and that's a big problem that people have been trying to solve. So here, for example, is a wind farm near Tehachapi Pass in California. So yeah, big problem with wind and solar is that they generate power when they generate power, not when you need power. And the electrical grid works on instant consumption tied to production. There's no buffer or storage. Solar power. Solar power is great and has been doing great recently. It's very promising source of reliable and economic energy. Solar panels got cheap, and we started generating tons of solar power. This is out of date in that some solar power, lots of solar power is in use now because the price on solar panels dropped, basically. But it has the fundamental problem of, again, you only have power when the sun is there. So your power is dependent on, the day-night cycle and the sun. So it's not generating any power at night. It's not generating any power. It's generating less power on a cloudy day, things like that. This is a problem that, again, would be solved by grid level storage, but that's a hard problem to solve, it turns out. Geothermal energy is great. So the geothermal energy is very site specific. You need some place that has a big enough temperature difference between the surface and deep underground. And if you know that's going to be the case, it costs a whole bunch of money to build a geothermal plant, but it costs basically nothing to run a geothermal. So high upfront cost, but if it's successful, quite efficient, long-term power generation. But most geothermal is in places where we know it will work. Because part of the problem is it's hard to know whether or not a site has a good difference in temperature. Like if you go somewhere like Iceland, which is sitting on a continental divide, so there's hot magma welling up underneath it, you can drill a geothermal well basically anywhere. And they do. They geothermally heat greenhouses there. Or Hawaii is a good place, because again, there's an upwelling of hot magma there, so is going to be a big temperature difference. But in theory, it could work lots of places. But what you need is, but the cost to drill is expensive, and you need to have successful, you need to know it's going to be a big temperature difference because it costs a lot for startup. So it depends on large natural change in temperature being present and accessible. There are people working on making it easier to make geothermal wells in more places by advancing drilling technology. Where instead of drilling with a drill bit to make a hole, they vaporize the dirt with a microwave mazer. I saw a recent video about the development of this technology. It's kind of insane. So they have the head of this thing going down, and it just vanishes several inches away. But that's still like in R&D. There's a company that's working on it, but they still haven't done anything in the field yet. But yeah, geothermal energy is great if you're in a place where it works. So for example, it's extensively used in Greenland, in Iceland, because Iceland is sitting on the mid-Atlantic ridge. So there's magma, the earth is splitting in half there. new ground is being formed. Well, it's where two continental plates are separating. So there is quite a bit of warm magma rising up. It's a good place for drilling. Here is one geothermal plant, Puna geothermal plant in Hawaii. So there's lots of places where geothermal energy would be great, where it's you have that big differential. Here is some natural geothermal energy being generated. This is an active volcanic flank of the Big Island of Hawaii. This is where lava is dumping in the ocean. Because Kilauea on Hawaii is like the most active is like the most continuously active volcano in the world. It's not like super dangerous or anything, because it just sort of steadily oozes out lava, but it is one of the most active. And one place where there are tremendous quantities of geothermal energy is the Yellowstone area, but not necessarily the best place. The practicalities of geothermal energy are complicated. Another source of energy that people would really like to use is tidal energy, because tidal energy is steady, reliable, and predictable. Tides go in and out twice a day. Nice and predictable. But if you're going to use tidal energy, you need to have things set up to handle bidirectional tidal currents, and you need to deal with things built in the ocean. And it turns out the ocean is a terrible place to build, mechanical turbines and things, because stuff grows on them. It's full of salt water, so stuff corrodes. It's just a kind of vicious place. But tidal currents have been generating energy along the Rance River in France since the 1960s. There's several other places where they've been using tidal currents. Again, it's locational. You want a place that has nice fast tides. But people have been working on using this. So the general idea is you put turbines underwater that can handle the flow, generate electricity in both directions as the current flows. And that generates power. Biofuels are fuels generated directly from plants. So things like corn, sugarcane, and other plants can be used to make ethanol, which is just alcohol. We use corn, sugarcane, and other plants to make ethanol for purposes of fuel, but we also use corn, sugarcane, and other plants to make ethanol for recreational purposes. That would be bourbon, rum, various other things. And ethanol can be mixed with gasoline and used as a fuel for cars. Pretty much all the gas you buy these days has got like 10, at least around Indiana, I think it's 10% ethanol. Depending on the plant process, there are some issues with this where you can end up actually using more energy in the production of the ethanol than gets supplied by burning the ethanol. This is a problem with certain plants and certain ways of producing it. Another thing that you can use as biofuel is just plant matter. You can burn it and use that to run a power plant. So biomass, any organic matter available on a renewable basis is considered biomass. These are industrial crops, wood, animal waste, municipal waste, aquatic plants, etc. You can burn this and generate electricity. So burning garbage to generate electricity is a pretty common thing in Europe. So that's the end of chapter 4. Here are the important equations. Work is force times distance. Kinetic energy is 1/2 mv squared. Work is equal to the change in kinetic energy, so 1/2 mv2 squared minus 1/2 mv1 squared. Potential energy is mgh for gravitational potential energy. In an ideal system, mechanical energy is conserved. So that's kinetic energy plus potential energy at time 1 equals kinetic energy plus potential energy at time 2. Power is work over time or energy over time, which is force times distance over time. And for something where you're converting you start with 0 kinetic energy and you're converting potential energy into kinetic energy, your velocity ends up being 2g delta h square root of that. This set of equations. And that's all for today.